Okay, so back a few days ago, I think it was Tuesday, we did latitude and longitude. And we filled in the top part of page 7 here. So if you don't have page 7 started, you probably were absent and you're going to need to get in these notes. Not only do you need these notes, this is the basics of latitude and longitude that honestly, for the most part, I think you should have known this before we even started in theory. If you didn't know it, there it is. Now that's what you needed. Now we're going to start some miscellaneous stuff, which is, like I said often, this is where we're going to 10th grade up latitude and longitude a little bit. And the first part is about finding your latitude. So right here where it says miscellaneous, we're going to title this Finding Latitude. And there is a trick. Have you guys ever heard, if you're lost in the woods, how can you get out of the woods? The North Star. Follow the North Star. What good is it going to do you, or how can you follow the North Star? Tell me about this North Star situation. What is the slaves also used the North Star to get out of the South? They followed the North Star. Any idea how or why that works? Okay, so one thing is you can see it. It's called the North Star. Why do you think it's called the North Star? First of all, it's north. Here's another fun fact, which I think you knew already. Can you see it if you live in the Southern Hemisphere? No. So it only works for if you are in the Northern Hemisphere. And remember, even though like the slaves were in the South, were they in the Southern Hemisphere? No, they were just in the South United States. That was a different situation. It's not the same as saying they were in the South, like the Southern Hemisphere. So they were able to follow the North Star north. It worked great for them because that was their goal, was to go north. For us, if we're lost in the woods, what good is going north going to do for you? Nothing really. I mean, here's how it works. So it'll only help you if your house or where you want to go is north of you. That's the only way following the North Star is going to get you there. But if you're lost, and you have no idea where you are, yeah. Oh, okay. Okay, that's another way. And it's a similar thing. Again, is that going to necessarily get you to your house? No. But by following the North Star or following a stream or a creek, what it's going to do is make sure you're not walking in circles. So if you keep the North Star lined up with you in front of you, you're at least walking a basically straight line. You're not walking in circles in the woods. So that will help you if you ever do need to. But the big problem is, well, okay, anybody know where the North Star is? Okay, it's in the north. If you're lost in the woods, do you know which way north is? Where it's flowing. I don't. I have no idea where north is if I'm lost in the woods. Okay, how about this? Maybe this isn't you had a drunken rager the night before and you had to wake up in the woods and you have no idea where you are.
Look for the North Star. It's sky on the top and the sun is rising.
Okay, so you thought about this a little bit.
I've been in this situation.
So you've been in this situation. All right. Too much information for me. Well, there's a trick for those of you who haven't been in this situation and haven't thought about it that much as Trenton apparently has. There's a trick, and the trick is the dippers. You guys know about constellations at least a little bit. There are constellations, you know that. Well, two of them are the dippers, the Big Dipper and the Little Dipper. Have you ever seen them? Yeah. Okay, so first of all, why do they call them dippers? Because I would call them a ladle, but that must not have been what they were called when they were made. So it's like a giant, the reason we call them a dipper is because you can dip into a liquid with them. They kind of look like a giant soup ladle. So first of all, that's why they're called dippers. Second, so if you've ever seen them, there are two. One's bigger than the other. The Little Dipper is actually kind of hard to find in the sky. The Big Dipper should be fairly easy for you to spot as long as it's a decent night out. And that's helpful because, so here's the Big Dipper. I have a picture of it here. See these two stars that I labeled pointer stars?
Yeah.
So the last two stars right here in the bucket of the dipper, they point right to the handle of the Little Dipper. And that first star in the handle of the Little Dipper is the North Star. And the reason this is super helpful is because if you are able to find the altitude of Polaris. Ooh, I just threw out a word there. Do you guys know what Polaris is? Yeah, it's a snowmobile company. It's the North Star. So that's the fancy name for North Star. So if you can find the altitude of Polaris, you have now found your latitude. Do you guys know what the word altitude means? Yep. If you did not know that, altitude means how high in the sky. So that's what altitude means, how high in the sky. And we measure this in degrees. So not degrees temperature, but degrees like an angle, which works conveniently because latitude is also measured in degrees. So if you can find the Big Dipper and it points to the handle of the Little Dipper, you have now found the North Star, Polaris, and you know your latitude. You estimate it. So for example, if I go outside and I find the Big Dipper and it points to the Little Dipper and it's directly over my head. So if the North Star is directly over my head, do you see how my arm is pointing straight up? Do you see, well, you can't see because I'm behind the desk, but do you see how my body, well, I guess my arm is making a 90-degree angle with the floor? See that? Arm, floor, straight out. I mean, it's down there, but I can't point it both at the same time. That means your latitude is 90 degrees. So if the North Star is directly overhead, it makes a 90-degree angle. I can draw a little stick figure here for you. So if we have the ground and Polaris is directly over that person's head, you can see that that would be a 90-degree angle. So if Polaris equals 90 degrees above your head, then you know your latitude equals 90 degrees. If the ground is here and you see Polaris here, and again, here's a person, there's that angle. Any idea what angle that is? What made you say 45? Because it's about half of 90. So see, there would be the 90. This is about half. So the altitude of Polaris is 45 degrees in the sky. What's their latitude? 45. It's that simple. Whatever the altitude of Polaris is equals your latitude. And I like to abbreviate that as altitude equals latitude. Guys, I can tell you right now, this will be on the Regents. There is not many things that I can confidently say will show up on the Regents. This is one of them. You must know that the altitude of Polaris equals the latitude of whoever's looking at it in the Northern Hemisphere. Let me explain why this works. To do this, I'm going to need you guys to stand up. Yep, all of you.
You're not
So, why does this work with Polaris and no other stars? Does anybody have any idea why this works for Polaris and no other stars? Nope. This is because, so the sky is kind of like our ceiling right here. The sky, the stars don't move from night to night. They don't really move. They actually look like they move, but the stars stay still, just like the ceiling is staying still. What I'd like you guys to do is, since the ceiling's standing still, what can we do to make it look like the ceiling's moving? Move! Spin. And since the earth spins, that's what I want you guys to do. So just to prove what I'm trying to talk about, one spin, please. One spin, look at the ceiling and see how it looks like the ceiling moves. Unless you are that dizzy of a person, don't.
Yeah.
Here's what I mean. So I'll show it to you. I'll sacrifice myself. So right now, I'm gonna stand over here so I don't bump into anything. Right now, that light is off to my right hand a little bit. But if I spin, is the light still to my right hand? Nope, it's behind me. And if I spin, it's over there on the left. And now it's in front of me. So did the ceiling really move? No, but did the ceiling look like it moved to me if I was standing there looking at it? It did. It looked like that light went from being on my right to being behind me, to being on my left, to being in front of me, back to being on my right. The ceiling stood still, but it looks like it changed compared to where I'm looking at. Now here's what I want you to do. I want you to find one thing and focus on that one object. So if you're near where they like cross, the ceiling tiles cross, look at that. If you can line up with like a smoke detector or whatever, that works out even better. So just pick one spot and focus on that one spot. I'm gonna focus on this projector. Go ahead and do one spin for me. So when you were focusing in on that one spot, did that spot look like it moved?
No.
No, but did the stuff around the spot move?
Yeah.
Yes. That should be how the stars work. The one star that you're focusing on that's directly above where you're rotating shouldn't move. Go ahead, you guys can sit down. Here's again what I'm getting at. The North Star, just like when you just lined yourself up with with a spot, the North Star is located directly over the North Pole. So it's like the ceiling is lined up. And it's located right here. So when the Earth spins, that North Star looks like it's holding still while all the other stars are around it are moving. So the North Star does not move in the sky. Now that even is true if I'm not directly above it, but where I'm spinning, so if I was able to spin like this, which I can't, but pointing right at the projector, so if I focus at the projector, and spin, the projector didn't move, but everything else around it moved. Polaris is the only star this is true for. It is the only star that is directly above the North Pole and it doesn't move every night. That's why the slaves used it. It was in the same spot every night. That's why you can use it because it's in the same spot every night and it's equal to your latitude. That is something you must know for the test, for a quiz, for a region. That the altitude of Polaris equals your latitude. You must know that. All right, so grab your reference table. Open it up to, what is it, page 3, the map of New York State. You could also use that one we colored on. I'll put that up on the board. And I'm going to tell you that I went on a trip around New York State and I looked up at the sky at night and I saw the altitude of Polaris was 42 degrees or around 42. Name a city I could have been in. Use your reference table. I was at 42. I saw altitude of Polaris was 42 degrees in the sky. So what do I know? If I know Polaris's altitude was 42 degrees in the sky, what else do I know? I know my latitude because altitude of Polaris equals your latitude. So if I saw Polaris 42 degrees in the sky, that means my latitude is 42 degrees in the sky. So that means I'm somewhere along this red line, really close to either Jamestown, Elmira, Binghamton, or even Slide Mounts right on 42. So those of you saying Buffalo, yes, it would be close, but is the altitude of Polaris in Buffalo equal to 42? Nope, it's a little bit higher. It's actually almost 43. So if I said I saw the altitude of Polaris to be 43, then it could have been near Buffalo or Niagara Falls or Rochester or Syracuse or Ithaca. What if I saw the altitude of Polaris at exactly 45 degrees? Where am I? Right on the border, right up here. I'm really close to Messina up here, practically to Canada. That is all you will definitely will need to know about that. Altitude of Polaris equals your latitude. They might give you an altitude of Polaris and ask you to tell you what city you could be in. That is one thing. Now we're going to do some fun facts about longitude. So longitude are the up and down lines, remember? Have you guys ever traveled to a place on a different line of longitude? So let me draw a couple in here just so we're close here at 80. Let me just draw these. Anybody ever been to an area that's a different longitude than us? Chris, where have you been? You tell me, is Florida on a different line of longitude than us? Here's us. Okay, but so let's go back to Florida first. So here's us in Buffalo, there's Florida. Is Florida on a different line of longitude than us? Not really. It might be off maybe by a degree or two, but for the most part, Florida lines up pretty darn close to us. But you've been to Texas. Is Texas on a different line of longitude? That's over here. Yeah, Texas is on a different line of longitude. Anybody been anywhere else on a different line of longitude?
Tennessee.
California. California's over here. Okay, so here's you're gonna lack my knowledge. I would need to see a map of the United States to be able to tell you where Tennessee is. Let me look. I know around where it is.
Yeah, Tennessee's right in the middle of Buffalo and Florida.
What? No, what did you just say?
Tennessee. Yeah, Tennessee counts. And here's why. So let me just. So here's Buffalo. Well, I guess it depends on where you're going in Tennessee. So Buffalo's over here. Yeah, everywhere. So yeah, Tennessee is on a different line of longitude. So Tennessee's probably like here-ish, somewhere in here. I don't know. Yeah, so Tennessee counts. Michigan, yep. So Michigan. So New York's here and Michigan is one of these guys over here. The green one. All right, I'll just take your word for it. There's Michigan. So Michigan over here. Wisconsin, yeah, they're even farther over here somewhere. Oh, okay. I was just to Oregon this summer. That's over here.
For what?
My brother lives there. So annoying.
You know, Goonies was filmed there?
Yeah, so we were right on the coast, right near where Goonies was filmed.
And Kindergarten.
I have never watched Goonies because I hate bad 80s movies. My husband loves them. Oh no, it's awful. It's
What?
freaking awful. Don't get me started.
What? Goonies?
Goonies, yeah, I hate it. Okay, so I have never watched it all the way through. It's too annoying and my husband's way too into it for me to get like, I can't get on board. Anyway, what is true about all of these places? Texas, Oregon, California, Wisconsin, I'm pretty sure Michigan, and I'm pretty sure Texas. Every time you go there, what do you have to do? Okay, well, you could fly.
Go there?
When you go there, what's different there? Okay, that's true too. Time zone, that's where I'm going. Yes, all of those other things were true as well, but not where I was going. Time zones. When you go to Florida, do you have to change your time zone? No. Because why? Because it's on the East Coast, same as us. But what else is true then? If it's on the East Coast, going to where I'm talking about now, Florida's the same longitude. If we're here, Florida's down there. Florida's on the same longitude as us. Is California and Oregon on the same longitude?
No.
Nope, they're way the heck over here. So what changes when you change your longitude? Time zones. That's what we need to add to this miscellaneous for longitude. So first thing is locations with the same longitude have the same time. Now, it's not every single, like, it's not like 79 has a different time than 80 and 81. They do go by groups. So the time zones are broken up into 24 time zones. Why do you think there's 24 time zones in, because there's 24 hours. Now, here's something you do need to know. Well, so if there are 24 time zones, how many degrees apart are they? So I'll put it up here and you can think. Time zones are blank degrees apart. So I want to fill in how many degrees are those time zones apart? Think this through. If there's 24 time zones. How many? Huh?
48.
No, not 60. How many degrees? How many close? How many degrees are? How many degrees are there in the whole Earth? 360. How do you get that so quick?
I was thinking about it.
You're already thinking about it. So there's one way, there's two. I saw you glance down at your reference table. Nowhere on here says 360 though.
So each side is 20.
There's 180 degrees on each side, plus how many degrees are there in a circle? 360. So the Earth has 360 degrees on it. 360 degrees. How many hours does it take to go those 360 degrees? 24, or that 24, because I just told you there were 24 time zones. 360 divided by 24 means the Earth rotates 15 degrees. Wow, why am I struggling? Every hour. So the time zones are 15 degrees apart. That is where I want to stop for today. So obviously you are ending about 10 minutes early. We will pick up on time zones again on Monday, but I did not want to do too much today so that everybody got through everything we needed to get through. Any questions yet? All right.